So this talk is really going to be a bit of back and forth between where we are heading towards 5G and what we learned in 4G and how 4G itself is evolving over time. And so the slides are kind of a mix and match of both. It also shows a little bit of state of the art. You'll see some slides over here based upon which you'll see demos later on in the afternoon. So that will probably give a little more of a context to the technology by itself. So let's start with what's our vision of 5G. Now, if you take a look at 4G, the very first industry workshop on 4G was held in 2004. This was 12 years back, actually about maybe 11 years back, November of 2004. And if you think back about where things were in 2004, there was no iPhone back then. We were about 2 years away from the Motorola Razr, which was a state of the art, if you remember those really thin phones. And mobile broadband by itself hadn't taken up at that point in time. The peak rates were in the order of around 300 kilobits per second or so, maybe a little bit more than that. And back then we said, okay, in 4G we're going to have very high data rates up to 300 megabits per second, which seemed like quite a lot. But the real focus was on mobile broadband. So we have a phone, we want to make it as fast as possible. Data is the big thing, and that's what we are interested in. And that was the vision back then. And as you can see, over time, mobile broadband has practically been the essence of 4G. All of us use it all the time. And it's gradually evolving over time. But this time, as we're looking at 5G, we're taking a look at the use cases beyond mobile broadband. I think that's the first thing that we're going to talk about in 5G. It's a large number of use cases, different kinds of industries and devices, not just smartphones, but different kinds of devices. If you think of any device that should be able to communicate with any other device, ranging from water meters to gas meters, other sensors, and to cars. So any kinds of devices, different user experiences, in the sense that we don't want to always be in the mobile broadband space, but sometimes there are things that we need to send out as soon as possible. So latency is one of the important criterions over there. It's a different kind of a user experience, an always-on user experience. And this enables different kinds of services. We're just getting started with the point where cellular systems are gradually percolating into different kinds of industries, not just into the traditional mobile operator space, but we're looking at things like industrial automation and other mission critical services. So 5G as a system is something that we want to design in such a way that it caters to all different kinds of services and different user experiences, all within the same network. So it is unified across different services and deployments. I'll come back to the spectrum part a little bit. Different ways of connecting. As a user, at this point in time, when you have a phone with you, actually most of us don't really care how we are connected to the network. We actually just crave for that connectivity, and that's pretty much it. Maybe it comes through a cellular connection, maybe it comes over Wi-Fi, maybe it's through some other sort of a connection. But at the end of the day, it's transparent to the user. So the idea is to have what we call as an edgeless connectivity, in the sense that we don't know exactly how we are connected, but it's all taken care of. There's a simple data plan with which we get served. And scalable to a very extreme variation of requirements. And that means at some point in time, maybe what we need is an extremely high data rate connection. At some other point in time, it's not really the data rate of the connection, but I want to get a message as soon as possible. Really can't wait for that. Or in some other situation, for example, in a water meter case, it's not about connectivity on an instantaneous basis or something that is on demand, but it's a water meter that wakes up once in a day, and it's supposed to last for 10 years, 7 to 10 years. So it's more about battery life and power consumption. So it's a different set of requirements, and it's an extreme variation of requirements. Our perspective or our design of 5G is such that it's a unified design that caters to a different variety of use cases. I'll come back to the spectrum types a little later, specifically on licensed versus unlicensed spectrum. Okay, so I kind of talked through some of this, but if you were to now take a look at the actual devices themselves, so we have the traditional smartphones and tablets for which we are going towards very high data rates. Now, let's take a look at the data rates in 4G. 4G data rates go anywhere from 300 megabits per second to a gigabit per second. But in 5G, we are looking at data rates which go way beyond that. We are looking at data rates about 5 to 10 gigabits per second. Average rates of hundreds of megabits per second on an average. And if you were to again step back in time, 15 years back, the average data rate most of us used to get was in the order of around 200 to 300 kilobits per second. And so that's about a 1,000-fold increase from the 3G days, and at least a 10-fold increase from the 4G days, at least. But these are the use cases that we already do today. There's 4K video, and it's a really high data rate requirement that drives this sort of a use case. The other one is the low latency and high reliability. Can we perform remote health monitoring with extremely low latency so that you're actually performing some sort of as an example, a surgical procedure, but it's done remotely, but you need extremely low latency and reliability is key. The messages themselves, the data rates themselves are pretty small, but it needs to be there with 99.59% reliability. And the latency that we are talking of is in the order of a millisecond or less, significantly lower than where we are today. The other use case is what I mentioned earlier about water meters. It's really about long battery life. If today you go and buy a battery or a AA battery in a store, the shelf life is about 5 years or so. Can we have a water meter that uses a certain kind of a battery, but then it only wakes up once a day and lasts for 5 years without charging? We charge our phones all the time today, but without charging for 5 years. And what kind of a system needs to be designed to make sure that these devices can operate that way? That's what we're looking at. Okay. And as we are working on 5G, LTE as a system itself is evolving. And we are working quite hard to take a look at LTE and see what else can we do beyond mobile broadband. So there are two distinct verbs that we'll use, Propel and Proliferate. We have LTE, which has now practically, it's there in every single smartphone. I mean, a good fraction of them, almost all of them these days have LTE in them. So the question is, what else can we do with mobile broadband in smartphones? And where else can we take LTE to new use cases? And I'll explain why this sort of a parallel evolution of LTE and introduction of 5G is going to happen over the next 5 years. So we're going to take a look at each of these specific topics a little more carefully. So let's start with mobile broadband first. The single most important feature with mobile broadband for LTE started with the ability of aggregating carriers. What that really means is, for example, when Verizon deployed LTE over here, this was back in December of 2010, that was the time that LTE was deployed. It was a 10 megahertz carrier in what is known as band 13, that's in 700 megahertz spectrum. If you remember, the auctions occurred back in 2006 time frame or so. That's 10 megahertz of spectrum. And then eventually, over time, Verizon got more spectrum, which was in band 4 or 2.1 gigahertz, so you add another carrier to it, 10 plus 10. And you get a little bit more than double the user experience, and that's because it's what is known as it's a statistical multiplexing. You can serve the user using one carrier or the other, so you sometimes get a better user experience than just double the capacity in that. But the ability to aggregate carriers, one on top of the other, in an asymmetric manner. Most of us download a lot more data than we upload, and so you want to have more bandwidth in the downlink than in the uplink. So the ability to aggregate carriers has been going on since about 2012 onwards. But what's interesting now, and we'll actually take a good look at that, is what sort of carriers are we aggregating? It used to be that we would take FTD carriers, two FTD carriers, and put them together. Then, about 3 years back, we decided that we want to have the ability to aggregate FTD and TDD carriers. The reason for that is spectrum comes in different flavors. In licensed spectrum, we have FTD and TDD carriers. In unlicensed spectrum, it's primarily TDD carriers. And so we want to have the flexibility to aggregate different kinds of carriers. So aggregating different kinds of carriers is an important part of LTE evolution, and you see that more often these days. In addition, what used to be a handful of carriers, 2 or 3 carriers, actually in the specification, LTE allows for aggregating up to 32 carriers. It's a very large amount of spectrum. Not that it's something that can be used, but it does give the flexibility to do that. 32 carriers is about 640 megahertz of spectrum. That's a little too, yeah.
You mentioned asymmetry earlier. With the whole change in focus from user data and mobile data to M2M and other use cases, is there any rethinking of the asymmetry and how asymmetrical things are?
Yes, I was going to actually touch upon that a little more with the FTD, TDD evolution part of it, but now is as good a time as any. So if you were to take a TDD carrier, traditionally, in fact, all deployed TDD systems have what is known as a fixed partitioning. You take TDD spectrum and let's say 50% of the time is downlink, the other 50% of the time is uplink. Typically, it's more like 70-30 because traffic tends to be a little more downlink asymmetric. But that's not necessarily the case in all geographical locations. For instance, if you're in a venue, in a stadium, actually most people are more in the mode of click and upload. Take pictures and upload to Facebook and so on. Actually, the traffic tends to be more uplink heavy than downlink. But that's just inside the stadium. The moment you go outside the stadium, it's a different asymmetry altogether. So the idea is to vary that asymmetry over time, the ability to change it over time, not just keep it static across geography. So it's not like the entire city of San Diego is going to have the same asymmetry, but in different regions, the asymmetry is different. Plus, in a given region, it can change over time. During daytime, it's a certain asymmetry. During nighttime, it's a different asymmetry. This is what is known as the adaptive uplink-downlink configuration. It's a key part of the standards right now. You can change it over time at very short time scales. We're talking of tens of milliseconds of time scales. Quite flexible in that sense. And it also allows us to, so coming back over here, so when you do that, then you have a notion of one of the carriers can be FTD, another carrier can be TDD, and a third carrier can be TDD, which is varying with this sort of a configuration. So it's a very good mix and match of different sorts of carriers. And speaking of TDD spectrum, about 3 years back, we started talking about LTE and unlicensed spectrum. There's a lot more that we'll talk about today. You'll see a demonstration of that, different versions of that. I want to spend some time on LTE and unlicensed in general. We started taking a look at what is the best way to utilize unlicensed spectrum. And we have Wi-Fi and unlicensed spectrum today, which actually continues to evolve, and we are heavily involved in that. But there are certain things that we bring to the table with LTE. And it's a different philosophy towards the usage of unlicensed spectrum in general. Cellular systems have been designed to thrive in interference. Spectrum has always been scarce. And so as you have more and more users, more cell sites, it tends to be interference limited. So there are all sorts of techniques in LTE which make sure that you have the best possible usage of unlicensed spectrum. There's interference management, interference mitigation in the network. There's what is known as rate control. Before you serve a user, you want to make sure that that's the right data rate at which you're serving the user, etc. These are the techniques that we brought to the table with LTE and unlicensed spectrum. And from that perspective, it's the best possible use case or usage of unlicensed spectrum, whenever possible. Whenever possible. We'll see a little bit more about that later. And finally, on antennas. So all of our phones, LTE enabled phones, they all use 2 antennas in the receiver, typically. Some of them use more than 2 antennas, but typically we use 2 antennas. And MIMO, LTE was the first cellular system that started with MIMO on the get-go. If you go back to 3G, whether it was UMTS or EVDO, we started with a non-MIMO configuration. But MIMO started from day 1 in LTE. But as we look at, we'll see a little bit more of this in the demo later, both for, actually you'll see more on the 5G demo. But Today we talk about what's called as massive MIMO. What that really means is in a handset we still have maybe 2 or 4 antennas. And you can see them, they're all internal antennas, but there's about 2 or 4 internal antennas. But the base station has got a very large number of antenna elements. It can range anywhere from 16 to 64 antenna elements. And the idea is to do beamforming, and what is known as 3D beamforming is a way, if this is the antenna, so if this is my palm of my hand, this is the antenna, what is called as a patch, you can actually serve users in elevation, up and down this way, or in azimuth, in this way. And so, if you think of what's known as pencil beamforming, you can have 5 users over there. Simultaneously, we are serving 5 users, but not in time or frequency, but in space. And so we get a much better improvement of the overall reuse of the system. So it leads to a significant capacity increase on the network. Each user gets the same data rate. Okay, so the user peak rates themselves are not increasing. On the other hand, the capacity of the entire network is increasing significantly with this. Okay, so now let's take a look at carrier aggregation a little more. So I mentioned the fact that up to 32 carriers are, you can aggregate that, and what's known as release 13, which is state of the art. Release 13 of LTE is the 5th release of LTE, and it's, is that true? 8, 9, 10, 11, 12, 13. Yeah, it's the 6th release actually. And that's being wrapped up sometime in the first half of this year. And we are on what is known as release 14 now, where there are additional enhancements coming in. This allows up to 640 megahertz of spectrum aggregation. So that's plenty. It's actually quite a lot at this point. But where is the spectrum coming from? Well, some of it is licensed spectrum for sure, but a good fraction of it is actually unlicensed spectrum. There's a large amount of spectrum that's available in unlicensed, especially in the 5 gigahertz band, and we should be able to use this. So for example, over here is the basic concepts of what is known as LAA and ELAA. A lot of acronyms, and that's the one thing that in standards process we managed to find acronyms which nobody knows why we came up with that. But LAA is license assisted access. And the idea is we have an anchor carrier which is on licensed spectrum. Everything else is unlicensed. ELAA is enhanced license assisted access. And the difference between these two is in LAA, we can only aggregate in the downlink. In ELAA, it's both downlink and uplink. You'll see this demo a little later today in the afternoon. I think it's at 1 o'clock or so, 2 o'clock maybe. And LWA is the ability to aggregate LTE and Wi-Fi. As I said, we are working also on Wi-Fi. And we also want to see the best possible combination of LTE and Wi-Fi, because all of our phones have both LTE and Wi-Fi in them. So what's the best way to aggregate both? One example of that is, most of you are probably on Wi-Fi right now, the guest Wi-Fi. But what that means is that all of your data is coming on that, and just your voice call is probably going to come over LTE. Just that, right? But your data is going to be either on one or the other, but not on both. And the idea of LWA or LTE Wi-Fi aggregation is, on a packet by packet basis, it can come either over LTE or Wi-Fi. So as you're walking around, you might just turn around that corner and see that the Wi-Fi coverage is pretty bad. That's okay. At that point in time, you get served using LTE. At a different point in time, Wi-Fi is better. Maybe you get served over Wi-Fi. So it's a way of opportunistically using the best of both technologies, as opposed to sticking to one or the other. And most of us have that sort of a situation wherein you're stuck on a bad Wi-Fi connection. You're stuck to it, but you're not getting enough data rate, you literally have to turn off the Wi-Fi connection. Yeah, you had a question.
How do you, is a determination of which one is better a standards-based thing, or is it just a vendor or carrier or the vendor level, or is it the user level?
It's more of a, so this is for, so obviously when we say LTE plus Wi-Fi aggregation, this is for a service provider who has both assets. So this would be a mobile operator. You got to have your LTE and some sort of a Wi-Fi connectivity. The hooks are in the standards. As in, how does a device supposed to, as you receive packets on both LTE and Wi-Fi, they're going to come out of order. So you want to be able to make sure that you reorder them and send them up the right way. The hooks, those sorts of hooks are in the standard. But the exact implementation is a function of even what the deployment is. For instance, in Korea, when you take a look at the backhaul connectivity, because it's possible that you have a Wi-Fi access point which is non-co-located from an LTE base station. The backhaul connectivity is fiber, so it's actually pretty tight connectivity. So you could do lots of other things over there. And in other places it might not be fiber connectivity, in which case you would rather go with the easy as it comes. Okay, I'm going to shape some traffic flow in one direction using Wi-Fi and the other one using LTE. And this is the notion that I was referring to just now when you have a non-co-located access point. So for instance, you can have two base stations and they both, the device is connected to both of them. And usually this is a configuration that we talk of when we have a different topology. So maybe the cell density is different between these two base stations. One of them happens to be in the lower frequencies, in the sub 1 gigahertz band. So we are talking of probably 1.5 to 2 kilometers intersite distances, very large cells. But in the higher bands, these cells can be much, the intersite distance can be much smaller, in the order of hundreds of meters. And typically this is for hotspot deployments. So the device is connected to both, with this cell, the macro cell, for instance, providing some sort of a blanket anchor coverage, so you never drop the call. And as you go closer to a hotspot, you actually get served using the other cell in addition to this cell. So that's the kind of a notion of dual connectivity. Now, let's talk a little bit more about what sorts of unlicensed spectrum do we have, and what's the in terms of what are the technologies that we can bring to the table with unlicensed. So these are the things that we are working on and driving them quite hard. I'll start from the top, where we have licensed spectrum which provides the anchor and anything else that can be tethered to that licensed carrier. We can have LTE in unlicensed as well, and we call that as license assisted access or LTE in unlicensed. We started using the phrase of LTE-U as just a generic term, LTE in unlicensed. The formal standards process, it's called as license assisted access or LAA. And this is where in a small cell we have both the licensed and the unlicensed carrier. That's that. And LWA is again for mobile operators who have carrier Wi-Fi deployments. Quite a few of them actually have it. And they happen to be treated in a very independent manner. And the idea is to aggregate them, aggregate both the technologies together in a way that's transparent to the user. And as a user is walking around, actually we don't even care how the packet actually came in. It could be over LTE at some point. It could be over Wi-Fi at a different point in time. But if you don't have any anchor carriers, today what we have is Wi-Fi. Personal area network kind of a situation here. 11AC is what is used predominantly these days. Most of our phones actually we use 11AC, 802.11ac. 11AX is being standardized as we speak. We are heavily involved in that process. And 11AY is a subsequent generation that's coming up after that. So this will continue. But in addition to that, back in a few months back, about 6 months back or so, we introduced multifier, which is based upon all the concepts that we talked about over here, which is LTE in unlicensed or LAA, except that there is no anchor carrier. So with an anchor carrier, this is how the situation is. You power on your phone, go through all the procedures of registering with the network, what is known as an acquisition, an access, and registration, and so on. All those procedures, they all go over the anchor carrier, but the unlicensed carrier is used only for a data booster. That's it. You just get your data there. But as you do mobility, that still goes over licensed anchor. In multifier, we've kind of cut the cord with the licensed spectrum completely. Now everything goes over unlicensed spectrum, including the data booster, along with the data booster. And you can see that, and we'll talk a little bit more on this, but it actually broadens the ecosystem way beyond where we are today. So it goes into new kinds of deployment models. And specifically when we talk about different hotspots, malls, venues, etc., where the density of users is quite large, that's where it's an interference limited system, and we believe that multifier brings in a lot of advantages to the table. Okay, and so why are we doing this? In addition to stating the fact that we've done a lot of our analysis which indicates that we can do better with LTE and unlicensed, based upon our simulations, our analysis, our test bed results, lab results, working with our partners in the industry, we see up to around 2x capacity increase depending upon how dense the network can be. And that's important to understand that there are times where the density of the users tends to be very large. Even though there's a large amount of spectrum, the number of users is so large that it becomes a co-channel deployment. In the same 20 megahertz channel, you see a large number of users or large number of access points. So this is the kind of a capacity increase that we see. In addition to range, how far can you go from your access point before you lose coverage? Now if you think about it, at home, I have, for example, a Wi-Fi access point at home, but by the time I'm outside into the driveway area, usually I've lost my coverage by that point in time. So that's what we're calling off as range. We can increase that quite a lot with LTE and unlicensed. The user experience is quite good with the licensed anchor because you never really drop the call. That's always there. It's just that we are using the unlicensed spectrum for data boost only. And from an operator standpoint, if any operator had a carrier grade Wi-Fi before, there would be literally two different networks. There's the Wi-Fi network and there's the LTE network. But now it's a single unified network. It makes it so much easier to manage all the devices out there. Managing the credentials, I have the same data plan. Sometimes I get served using Wi-Fi, sometimes over LTE, but it's all bundled up together. And it's a common management of that. But the most important question, as we started this about 3 years back, was, oh, there's already Wi-Fi in unlicensed spectrum. If you're going to bring in LTE into unlicensed spectrum, oh, that's going to not go work very well for Wi-Fi. And we've spent a lot of time, about 3 years now, in doing tests, in convincing first ourselves, making sure that LTE coexists very well with Wi-Fi, and then convincing others that this is indeed the case. And all the technology elements are there as a part of LTE and unlicensed. And just to give you like a brief anecdote, when the standards process, there's usually two phases in a standards process. What's called as a study item, wherein everyone studies the technology and making sure that we're on the right track. And then what's called as a work item, wherein you actually write down the letter of the spec. So the first one is more like the spirit of the spec and making sure that we are on the right track. As a part of that, I believe around more than 15 companies, I think the final count was about 19 companies or so, submitted results which indicated that there is always good and fair coexistence with Wi-Fi. It's important to understand that it's not like just a handful of companies that are doing this, but it's an industry-wide consensus, at least from the cellular operators. Of course, there are still a lot of others who believe that we need to do more tests, and we continue to do more tests. Yeah.
About 6 months ago, I think there was some talk about changes in making LBT mandatory or recommended, because I know in some geographies it's mandatory, others it's up to the goodwill of the carrier, which is questionable around here anyway. Any changes?
Yeah, so I can actually talk about that a little more. So first of all, regions such as Europe and Japan, they have a very strict interpretation of listen before talk, wherein any entity, before it transmits, it has to perform energy measurements over small chunks of time, ranging from 9 microseconds to 20 microseconds. And you kind of say a go, no go, do I hear anyone else? If the answer is no, then I kind of do that over a period of time, and if it looks good enough, I'm going to actually go ahead and transmit. So that's a strict interpretation of listen before talk. And that's there in Europe, Japan, and a few other countries. In the US, we have a little bit more of a relaxed listen before talk capability, in the sense that it says that there are certain nicety rules about the transmission power. You cannot transmit at a very high transmit power and so on, but the strict requirements are not there, which is the energy detection part of it. That being said, and this is important to understand, when we talk about LTE-U, or what you saw with our work with Verizon on this matter, we would still prefer to call that as a listen before talk, because we do a lot of techniques in which, in effect, we are sniffing for Wi-Fi channels and seeing, okay, who's using what and who's not using, which is a more appropriate channel. And then making sure that there is a fair share of the medium that's taken up by LTE and unlicensed. So even though the regulations don't call for that energy detection part of it, the actual LTE-U specifications are written in such a way that that's exactly what we do, in the sense that it's not in terms of energy detection, but in terms of the fair share of the medium. You take a small chunk of time, you don't take it all the time, you don't take up one channel and all the time. So in that sense, we would still call it in the spirit of listen before talk, but it's not the energy detection part of it, but it still perfectly complies with regulations.
Is it mandatory?
The energy detection part of it is not mandated as far as FCC.
Any of it?
But there are other parts which are mandated, yes. The transmit power and the power spectral density and so on. Okay. There is one other thing I wanted to mention over here. In addition to this, there is, so there are the 3GPP specifications and LTE-U specifications. On top of that, there are regulatory specifications in ETSI, which dictate what the rules are. So we are also working with ETSI to make sure that the rules are uniformly applied across all the technologies. It's only fair so that both LTE and Wi-Fi, we can actually design the system in the right way. So there is work on that as well in ETSI, and that work should be completed sometime this year. As far as LAA is concerned, it was a part of release 13. Those specifications are basically complete, as I just mentioned, and we are moving on to release 14, wherein we have both downlink and uplink. So what used to be the LBT, the listen before talk capability, which was implemented only in base stations, because the devices are just receiving, they're not transmitting, so they don't have to do anything on this sort. That's in release 13. But in release 14, with both devices and base stations transmitting an unlicensed spectrum, there are certain LBT algorithms and rules that have to be applied in the devices as well. So speaking of Europe, we've been doing a lot of tests actually in San Diego, and we did a pretty good set of test cases spanning over a few weeks with a major European MNO in late fall. And we did a large number of tests to make sure that we can test the coexistence of LTE and Wi-Fi, compare the coverage of LTE and Wi-Fi. By the way, every time we say Wi-Fi there, we are talking of 11AC, so just to keep that in mind. But it is state-of-the-art 11AC. And the coverage, the capacity, and the coexistence. And we have our Qualcomm offices in Nuremberg. It's a quiet place, and it's a place where we can actually do this sort of a test. And so we tested out different technologies, LTE with the anchor carrier, and then having LAA versus LWA, and then Wi-Fi. And it's a mix and match of test cases that we looked at, indoor and outdoor deployment, in a van, stationary devices, moving devices. You're in a van, you're gradually driving around, and just looking at how you're getting served, whether it's on Wi-Fi or on LTE. Handover between cells. Remember that the anchor carrier is still in licensed spectrum, so you never really drop the call, and making sure that that's still the case. And what we observed is that, at least in these sorts of tests, there was a very good and fair coexistence between LAA and Wi-Fi. And the coverage and capacity benefits over LAA and Wi-Fi in these tests were actually shown. And this was a first step towards the commercial as operators get more and more comfortable, but this would be a very good and first step in terms of proving this in an over-the-air environment. And yeah, this, by the way, is just a picture of how the rooftop antennas work. This is, you'll see something very similar to this later on today in the afternoon, and that's based upon our test bed over here. So we have two test beds, one in San Diego, one in Nuremberg. And these are two buildings that our offices are in, and on the rooftop there are two base stations here and two more base stations. So you're looking at 4 base stations outdoor, one which is indoor, and then there are 4 devices over here. One of them happens to be a van. It's a device inside a van. So it's about 8 devices, all in the same 20 megahertz channel. And this is important. They're not talking of channel selection and therefore picking the right appropriate channel. They're all exactly in the same channel. And so it's a co-channel coexistence test that we are talking about. Okay. So let me switch gears towards what's called beamforming with massive MIMO. And I mentioned the fact that we have what is called as 3D beamforming, and actually in the specs we don't call it as 3D beamforming, it's full dimension MIMO. And the reason it's called as full dimension is because we're using the azimuth, so we're just in this direction, steering in azimuth direction, and elevation. We use both these dimensions to serve users. And because this is a very good usage of the spectrum in terms of spatial separation, we get a much bigger capacity increase over a network capacity. It's not for each user still gets the same peak rate, but it's a summation of the data rates across all these three users that gets us to a larger capacity. And we'll see that this is one of the things that actually is setting the path towards 5G. I have about 25 more minutes and still on slide number 10, but I think we can do that. I'll speak faster when I see a slide in which I probably have talked a little bit more. But you'll see that this is an important component of 5G. And one of the reasons for that, maybe I can just pause here right now, is the bands that are being considered for 5G span anywhere from what is called a sub 6 gigahertz, so anything in the below 6 gigahertz band, to up to 60 gigahertz and even beyond. And the initial deployments, more likely than not, will be in the 3+ gigahertz range. So because we are starting off a little higher in the carrier frequency, you've got to make sure that the coverage is still good. And if you want a good coverage, then we need a larger number of antennas in the base station for sure. So that's like a starting point for this. With just 2 transmit and 2 receive antennas, it'll work in the lower bands, but not necessarily in the higher bands. For ubiquitous coverage, we need something better than that. Okay, so switching gears to beyond mobile broadband now. How about lower latency? LTE latency is in the order of tens of milliseconds today. Even now, if you, for example, want to go to a website, it takes a couple of seconds before it refreshes, sometimes even longer, depending upon how it is. But say that we had, and we just talked about the fact that we get a gigabit per second in our phones. So say that we have a gigabit per second. Does it mean that we'll have that instantaneous on experience? It's not obvious. And one of the reasons for that is these websites, I mean, when you take a look at HTTP, the underlying protocol is TCP. And you got to make sure that the delay is small enough when you increase the data rate quite a lot. And so edge caching is an important direction that a lot of vendors and operators are thinking of. In other words, take the top 1,000 websites and cache them in the base station or some sort of a central location, but not beyond their core network. Or take the top 500 YouTube videos and kind of cache them in a certain way. What that means is that when you click on, say, okay, I do CNN.com, and then I just get this instantaneous experience, and that's because you're not incurring the entire latency of the network. And now what's left is the latency that's in the air link. And we want to make sure that we can still improve the performance over there by reducing the air link latency quite a lot, from 20 milliseconds to substantially less than that. In the limit all the way down to 1 millisecond, but typically in the order of less than 10 milliseconds. It's also quite useful for some of the real-time applications when you have the call setup delays. Yeah.
When you say improve throughput performance for by decreasing latency, do you mean performance from a user perspective or performance as in network utilization from a carrier perspective?
Both. From a user perspective, we might be trashing the wheels on the air link at like 1 gigabit per second, but the application is probably like at half of that data rate. And that's because we're not actually quite doing the right thing. So we want to match the air link and the application rate. At the end of the day, the user experience doesn't care about the air link data rate. It's about, okay, if I do a speed test, do I get a gigabit per second? You might not get it unless you do some of these techniques. And the other part is latency critical applications, and I'll speak a little bit more about V2X, vehicular communications. These are applications wherein we want to reduce the latency of message exchange. It's not about the high data rates, but it's really more about latency requirements. Command and control of drones. This is an interesting one. Maybe about 3 years back, that's the first time we flew our LTE drone in our test bed. It was just for fun in summer. Because you buy a drone, it's a Wi-Fi drone, and it's range limited, it only goes so far. And you said, no, hang on, I mean, in the limit, that can just be a flying smartphone. So all we really need to do is have an LTE modem in it, and it can perform handovers like anything else. Yeah, it did, and actually it worked quite well. And that is like a starting point. Of course, there's a lot more work that's needed. But now the question is, okay, if I wanted to control that drone, do I have to have my device and then control it? Can I be in the lab or in some sort of a command and control center with which you can now control fleets of drones? Then what sort of latency is needed? Because once I send a command, it needs to react to it in a certain way. A lot of these use cases drive the latency requirements. It's not in the sub-millisecond range, but still it's somewhat of a lower latency than where we are today. So it's kind of a important area that we are looking at. We don't have all the answers yet, but it's an important research area for us. So speaking of proliferation and V2X, today LTE is deployed all the way from, I think the lowest band is 700 megahertz, I think band 704 megahertz or so. And the highest band at which LTE is deployed is probably in the 3.5 range, 3.5 gigahertz range. So it's in a large number of deployments in different bands. And now the question is, what else can we use this? So let's take a little bit of time on Internet of Things. LTE IoT or Internet of Things, the specification work started about 2 years back, and today there are two ways of looking at Internet of Things, IoT and LTE. IoT devices can be anything ranging from smartwatches all the way to water meters. So the smartwatches are the so-called high performance ones. They're not extremely high data rates, by the way, but there are other characteristics that are important, such as high battery life, being able to be connected, but at the same time not connected all the time because that can drain your battery in a certain way. That's the high performance ones. And the low power and low complexity ones, such as metering services, water and gas meters, I mentioned that. And sometimes even in our watches, so for example, if you have any of the existing smart watches, the display is usually off, and there is a certain duty cycle at which it wakes up, it looks for an incoming voice call, and if there is nothing else, it goes back to sleep, but trying to extend that to a slightly longer duration. So there are two flavors of it in the specification work. There's one where the peak rate is only 1 megabit per second. Just keep that in mind. As I said earlier, about 45 minutes back, when we started LTE, we said 300 megabits per second was the data rates that we were looking at. So today we are talking about 1 megabit per second. That's like the peak rate that we can get. That's good enough on a watch. It's more than enough. And then another tier of devices which are significantly lower than that, down to 10 kilobits per second. And now it's a little bit of a throwback in time, in the sense that IS-95 back in the mid-90s was at 9.6 kilobits per second. And these devices are 10 kilobits per second. And these are water meters. Their only job is to wake up once a day, sometime late in the night, send out a couple of bytes of data and go back to sleep. That's it. Latency is not an important criterion there at all. Power is king. That's the only thing that matters. So, and data rates don't matter. It's, you can send that message over a few seconds and go back to sleep, and that's perfectly fine. So these are two different tiers of devices, but they exist in the same spectrum and in the same network as all the other mobile broadband devices. So if there's an operator who's deployed LTE, that operator will serve users who have smartphones and smart meters and watches and etc. So it's the same network and the same system that caters to different kinds of devices. The other one that's coming up, I'll spend a little bit more time on V2X, but let's finish a couple of these over here. Let's start with digital TV broadcasting. Now this is an important and interesting concept that's evolving. It's starting in Europe first. There's a large amount of spectrum that's available in the 600 megahertz band. It's called the UHF band, between 470 to 700 megahertz. And it's spectrum that's usually used by broadcasters. But there are certain trends in TV content consumption. First of all, more and more users are interested in consuming content on the go. And what that means is that we want to have the ability to watch that regardless of whether we have a strict TV reception at that point or not. So that's one. And the second thing is that as the content itself is being consumed, there is a blurring of the way we think of content. For example, I might have signed up for HBO Now. Previously, I would have had to enter with what was called as HBO Go. I would have had to enter, okay, who's your cable provider? So I write down, okay, Time Warner Cable, my username and password. Then and only then I get that. But now you might have a direct relationship with the content provider, and it's up to the content provider to figure out who's the best service provider to serve you. I pay my $10 a month and then it works. And broadcasting is also, there are broadcasters who are thinking of how do we actually make such a different perspective on broadcasting. How do we actually take that and use the cellular services to serve users, because those are the mobile users. And so it's a digital TV via LTE broadcast is a new concept that we are working on both in the standards process and working with regulators and operators. There's a difference in the topologies. One of them is what is called a high power, high tower topology. So you're looking at 100 meters antenna heights and typically tens of kilowatts of transmission power, maybe a couple of sites in an entire city, compared to a mobile network where it's low tower in the sense that we are looking at less than 30 meters of antenna height, 10 to 30 meters, and transmission powers which are in the order of 40 watts or so, not more than that. But for mobile devices, that low power, low tower topology is the way to do this. So if content has to be delivered to mobile users, we believe that LTE provides a lot of benefits. And we have a few results on that we actually keep talking about in standards process. But yeah, that's where the differences really start cropping up.
When you say bring mobility into it, do you mean unidirectional or bidirectional transmissions?
Even for unidirectional, even for just broadcast itself, so nothing in return. Even though content providers are interested more in interactive content, right? I mean, the only time we all watch something live is, well, live sports is probably the best possible examples. News clips and live sports are the big ones. But most of the other content, you want to watch it whenever you want to watch it. So there is an interactive process over there too. Okay, proximal awareness or LTE direct. This is another example wherein devices can discover each other and potentially communicate with each other, which sets the trend towards LTE V2X. So
before you move on,
yeah.
Do you have any update on low power protocol for IoT?
Yeah, actually I was just getting to that part over there, over here. This is the LTE IoT space over here. The protocols are constructed, these are the ones that are being defined in the LTE-M or narrowband IoT. These are the two categories of devices in LTE IoT. This is where we have the protocols for what is known as DRX cycles, the ability to sleep for extended periods of time when in connected state and in idle state, and state management. When a device wakes up once a day, it doesn't have to go through an entire process of registration with the network and getting authenticated, and after a few seconds of that, finally send a couple of bytes of data. And this is known as a power save mode state management, which is actually done in the network itself. This is a part of this entire design, which has been standardized in Release 13. Okay. All right. I'm going to actually talk a little bit more on V2X, so let me just skip to that. V2X. V2X is a moniker which has two flavors to it: vehicle-to-vehicle communication and vehicle-to-infrastructure. The idea is to have cars communicating with each other, not necessarily listening to a feedback, but simply indicating their own KPIs. I'm heading in this direction, this is my speed and a few other KPIs, and used for a lot of these messages are used for safety, really for safety protocols. So if you think about V2V, we are looking at not just radar-based platooning and so on, it's a lot more than that. A classical example could be in an urban scenario when you have two cars which are approaching an intersection. One of the cars has a green light and you're actually moving ahead, but unknown to you, the other car, maybe there's something wrong with the driver and that car is unable to stop and it's going to pass that red light. These cars can actually immediately communicate that information with each other at a much longer range and be able to take appropriate measures for that. It also sets the ground for if you introduce LTE in a car, and you see that more and more with connected cars, in addition to the basics of infotainment and apps, what else can we bring to the table? And vehicular safety is an important direction. This is a release 14 work item that's started just now, specifically about cars communicating with each other using LTE. This is a direct communication between two vehicles, which needs to be a baseline when you don't have any infrastructure coverage. But then this can always be augmented with vehicle to infrastructure, because you might get other messages coming from a base station. The base station is on top of a light pole and so on. Now keep in mind, and I want to actually emphasize this further, while V2V is it's an important element towards safety, it's not the only thing. Why is that? That's because say that you're driving and a kid immediately comes in front of you. You can't really expect that kid to have a smartphone which is sending out a beacon that somehow is detected by the car and then it took an evasive measure and stopped. No. You got to augment that process along with cameras and sensors and onboard processing. So it's a complete package of what we call as this on-device intelligence, wherein we are actually bringing in concepts of computer vision and onboard processing with all the cameras around the car, in addition to the vehicle-to-vehicle communication and V2I, with diagnostics being exchanged across cars. Yeah.
Is this does this include ADAS functionality, or is it?
Yeah, this part of it.
Okay.
Yes. Yeah, exactly. So this part is the one that is being standardized. Obviously, this part is not being standardized in a forum like 3GPP. That's a very radio-centric forum. This is what is being standardized, the vehicle-to-vehicle part of it and so on. And inside the car, we might still want to have a Wi-Fi hotspot. So you have a single device that actually does V2V and V2I communications, cameras and onboard sensor processing, and then a Wi-Fi hotspot so that you still have coverage inside the car or for any device that actually comes in. So it's a combination of different technologies over here that are a part of that V2V and V2I space. Okay, I mentioned this part already, so I'm going to skip this, proximal awareness and digital TV broadcasting. Okay, let's talk a little bit about timelines. So, we started this, the whole conversation about 5G as to where this is going, but meanwhile there's a proliferation of use cases with LTE. 5G standards process is beginning now, officially. It starts in, I think, less than a month now. And it's going to take about 3 years. By second half of 2018, the standards process will be complete. So all things remaining the same, when we talk of the first deployments, well, if you were to go with that standards process, then the first deployments will be in the late 2019, early 2020 timeframe. That's about 4 years away, but in the meantime, there is a proliferation of all these different kinds of both use cases in mobile broadband and non-mobile broadband that is sustaining the cellular technologies. But another way of looking at that is, all these technologies are also paving the path towards what will be the first deployment of 5G. There will be massive MIMO in 5G starting from day one, most likely. Low latency will be an important part of it. Similarly, device-to-device communication, the marriage of licensed and unlicensed spectrum starting from day one. I mean, if you think about it, in LTE, we decided to add unlicensed spectrum a little later. But licensed and unlicensed spectrum will be there from day one in 5G. So all these things are paving the way towards the deployment, the first deployment of 5G in that time frame. Our overall test beds, we've always spent a lot of time in our research labs first, then doing the tests in our OTA test bed, then with operators, sometimes even before we bring a technology to the standards process. So an example of that is, if you take a look at our work in the standards process of LTE Advanced and LTE Direct, LTE Unlicensed, a lot of these, way before LTE Unlicensed even started in the standards process, we started showcasing these demos in Mobile World Congress, which that's like the typical time frame we do this. And you'll be seeing this demo, both LTE LAA with uplink and downlink and multiplier. This demo is actually going to be shown later on this month in Mobile World Congress, but you'll be seeing that today. But the work just started. It just started in the standards process. But we've built up our prototypes, we are pretty confident about how it works. We are also learning in the process, there are things that we learn, and whatever lessons we learn, we incorporate that back into the standards process. That's why we kind of stand by that. And this is the research part of it. From a commercialization standpoint, if I take a look at our chipsets, these chipsets are the ones which are the first, industry first in terms of the cutting edge technology, ranging from the very first LTE Advanced solution with carrier aggregation to the first modem that supports LTE unlicensed, and narrowband IoT and LTE-M, which is the higher tier of IoT devices. Okay, I want to spend about 5 minutes on 5G. As I mentioned, 5G system is something that needs to take into account these variety of use cases and making sure that we have a flexible air interface that can cater towards everything. So it's scalable, as I said, towards extreme variations and requirements. But there is something interesting in 5G. Our version, and it's also an industry consensus in some sense, is 5G is going to be OFDM based. Why is that important, by the way? Actually, it's a very first time that we are doing a change in generation, 4G to 5G in this case, where we're not changing the basics of the air interface. For example, when we went from first 1G to 2G, it was an analog to digital transition, early 90s. 2G to 3G was a transition from what used to be GSM and TDM systems to CDMA. 3G was about CDMA. The transition from 3G to 4G, we changed the air interface, and it was OFDMA. OFDM was mainstream. 4G to 5G, it's still OFDM. It's still OFDM based, and that's an important part that needs a little bit of thinking as to why is that. The reason why we continue to prefer OFDM is it has proven to be quite flexible in terms of scalability. We can go up and down in bandwidth, and we can multiplex users, services in different ways in a very elegant manner. So it remains an OFDM based physical layer and MAC. We've done a lot of work on millimeter wave. These days you see a lot more of that. You'll see one of the demos coming up after lunch. And millimeter wave is a 28 gigahertz system. This is a pretty interesting technology that we are looking at as to how we can go to extremely high data rates and serve a large number of users. So let me explain this part and then jump to millimeter wave. We have another 3 minutes or so. OFDM based waveform, but it's highly flexible in terms of multiplexing different services and users. So if you were to take this in time and this in frequency, different sets of users, services, and features coexist in different units over here. So in time they can be multiplexed, or in frequency across different tones they can be multiplexed. It also brings about a very elegant way of doing massive MIMO and millimeter wave. So